want to start with the derivative at 0. Okay. The fifth derivative of a fourth degree polynomial, what will that always be? A constant, right? Everyone agree? What constant?
4 times 3.
Be 8.
I don't know. I don't know. I'm not sure. Okay, let's just say it's C, right? Right? Say you don't know. Then the fourth derivative at 0 is 5, right? So what does that mean C has to be? 5. Yes, okay. So if the fourth derivative is 5, the number 5, then what is the third derivative? 5x plus C? Could you find C? Okay, walk up. I got you started. Now you finish. Okay, so I got you started, but let's keep going. First of all, what's the C here on P triple prime? How do you know? Does everyone agree? Okay, and now I'm going to find the second derivative by anti-differentiating. 5 over 2 x squared, everyone agree with that? Plus 4x plus C. Any questions? What is C? C is 3. How do you know? Okay. Is it okay if that's the last one I show plus C on and we just start putting in the C as we go? Okay. The first derivative would be, and I'm going to, just for fun, leave that written as 2 times 3. And what would this one be plus? Plus 2. And that means P would be 5x to the 4th over 2 times 3 times 4. Everyone agree with that? Plus 4x cubed over 2 times 3. Right? Plus 3x squared over 2. Plus 2x. Plus C, and what would the C be on this one? 1. What? I put plus E. Oh, that's just not E, the number E. E and another constant. A, B, C, D, E constants. Okay. Say we had the fifth derivative. Say it wasn't a fourth degree polynomial. Say it was a fifth degree polynomial and we had the fifth derivative. What do you think the polynomial would have looked like? What additional term would you have if you'd had another derivative? What's the pattern, in other words? You would have x to the 5th over 5 factorial. And then the number in front of the x, where did those come from? The derivatives, right? The derivative at 0 from each term. Does everyone agree? Those were all of these numbers. 1, 2, 3, 4, 5. They gave us those. So, remember, our goal is to construct a polynomial to fit a function, right? So I want to construct a fourth degree polynomial that matches this function by using successive derivatives of x. Now, we did it a different way the other day. We actually looked at one similar to this one. I don't think we actually did 1 plus x. I'm not sure. I can't remember. But I want to do this like we did the bell ringer instead of like we did on Monday or Tuesday and Wednesday. Can I find f prime of 0? Well, can I find f of 0, first of all? What is f of 0? Can I find f prime of 0? First of all, what is f prime of x? Well, first I said, what is f prime of x? But then f prime of 0 would be 1. Could I find the second derivative? A couple of ways you could do it. If you use a power rule, if you call this to the negative first power, you negative 1. Oh, yes, it would. Thank you. Plug in 0 and I get negative 1. Okay. Just for fun, I'm going to rewrite this. I did the last one in my head and I feel like I might have lost a couple of you. Isn't this that? So the third derivative would be positive 2 times 1 plus x to the negative 3. So the third derivative at 0 would be 2. Everyone agree? And the fourth derivative. Quick mental note, how many derivatives did we need to get the fourth derivative on the last one, or to get the fourth degree polynomial on the last one? 4 derivatives was enough, right? So this will be my last derivative. Yes. Did I do something wrong?
On the third derivative, would the 2 be negative?
Negative times a negative.
Oh.
But good question. I definitely make mistakes, as you know, so ask. Always ask that question. Okay, put 0 in and I get negative 6. Could we do the same thing we did on the last slide, except this time we found the derivatives? Except I want to shortcut it this time because I learned a pattern last time. And I'm going to put f of x is approximately, because this is an approximation of the polynomial. So I want to take you back to big picture because it's easy with series to get lost in what we're doing. Our goal is to create a polynomial that matches this function, natural log. Remember, natural log is a hard function to work with. I have no idea what the natural log of 2 is. You know what I mean? But if I can create a polynomial that's close, then I can find values of natural log that are close. So that's what our goal is. So f of x would be approximately a fourth degree approximation of that. Very good. Plus what? Plus plus
X.
1x plus 0. We have created a polynomial that is an approximation for natural log of 1 plus x.
Why do you use natural logs much more than actual logs?
E is a common place where we need natural log. E is a common base, so natural log is a common logarithm. Very similar to base 10, it comes up a lot in the real world. Use the method from the previous example to do the same thing for this function. So Joseph, this is kind of what your brain was doing. You were finding successive derivatives. Yep, but you had to go back to find the. Mm-hmm. You just didn't know the 24 or the 4 factorial part. Good derivative practice. It's been a while. I am doing a little simplification. Why would I go ahead and do simplification? Yeah, I've got to do a second derivative. So even though normally I would leave it, I'm going to go ahead and do some. Unfortunately, only to number 2. Do what? Oh, it's 5 halves. Sorry. Good call. Yep. How far? After 3, you either have to write a digit 4 or do Roman numerals. Right, tick marks.
You have to multiply by them. Oh, you did.
Oh, thank you. Good call. Okay. So, f of 0 is 1. Just 1. Positive 1. You only put a plus or minus when you're solving, not just when you're doing a square root, it is only a positive value. F prime of 0 would be 1. Here. Oh wait, no. Yeah, F prime of 0.
It's 1 over 1. because it's
One.
2 plus 1.
No, it's 0 plus 1.
Oh, we're doing 0?
Yep.
So
F double prime of 0 is -1. F triple prime of 0 is 3. Is that right? And the fourth derivative at 0 is, it's a fraction, isn't it?
Wasn't it just
should just be negative.
Oh, good. Oh, yeah, because the 2. -15. Okay. Hopefully you'll have those numbers where you can see them on your paper. So, what would the fourth degree polynomial be that approximates f of x?
Minus x squared over 2 plus x plus 1.
Is that what everyone got? Okay. So, that brings us to a theorem. The series that we just created is called a polynomial, Taylor series polynomial, centered at 0. When it is centered at 0, it's also sometimes called a Mclaren series. Taylor series can be centered elsewhere other than at 0, which we will talk about in a moment. So, Mclaren series or a Taylor polynomial centered at 0. If you have a function that has derivatives of all orders on some open interval containing 0, the Taylor series generated by f at 0 is given by f of x equals f of 0 plus f prime of 0 times x plus f prime of 0 times x squared divided by 2 factorial plus f triple prime of 0 times x cubed divided by 3 factorial, all the way up to the nth derivative at 0 divided by n factorial times x to the n. And so we could create a polynomial of any degree. To the right, you will see the summation notation of a Taylor series polynomial. It's the kth derivative at 0 divided by k factorial times x to the k, summed up from k equals 0 to infinity. A partial sum is just if you stopped at anywhere along the way and didn't go to infinity. This is a polynomial that will approximate a curve. Any curve. Now, before I do the one down there on example 3, I want you to glance back in your notes at the ones we created on, well, you may, or glance at your, that calculus helper. You remember all those sequences I showed you the other day? All those series I showed you the other day. Glance at those really quick. Do the sine one, which is the one we did in class. What's sine of 0? What is sine of 0? 0. So a term completely goes away. You see how sine only does the odd portions, right? Because every other derivative, sine of 0, 0. What's cosine of 0? 1. So you would have +1 but -1 sometimes on some of the derivatives. So do you see how those could be generated with this formula? Those are just the Taylor series polynomials generated from this formula. Now, they are so commonly used that we will memorize those. But if you ever forgot one and you're on the AP exam, are you out of luck? If you know the Taylor series polynomial expansion, you could recreate any of those. This is how you can create a Taylor or a series that will give you an approximation for any function. So I want to create a fifth degree Taylor polynomial for e to the 2x. There are two ways to do this. I'm going to work as if I know nothing and use the formula. However, if you had the e to the x expansion memorized, you could also replace all of the x's with 2x. So there are two ways you can generate a polynomial for e to the 2x. They will be the same answer. One will look slightly different. Yes? After this period? I think that's what he said. Okay. If I know nothing, then I have to do how many derivatives? 5. If I have the formula memorized, I could just plug in the 2x. And so we don't have formulas memorized yet. So we'll pretend we don't, but you can see how on the AP exam it would save you a lot of time if you did have the formula memorized, because it's going to take me a minute to do 5 derivatives. Not forever, but a minute. First derivative would be 2e to the 2x. Everyone agree? Second derivative. Yes. Because I need a fifth degree polynomial. 4e to the 2x. Am I going too fast? How are we doing? Good? Okay. I am aiming for starting at Wednesday next week. We'll see. I have to give you 2 weeks before. Well, I don't have to, but I like to give you 2 weeks before the end of the 9 weeks. No, not next Wednesday. The following, the 24th. We need to start it by the 24th. If we can start it before, then we will. We'll see where I get to. No, it would be. I thought it was, but it's the 24th. Because we need 2 weeks to get it in, and 9 weeks ends on the 11th. So I need it. I'm aiming for that Wednesday so that the 9th we have it done. That's my goal. We'll see how that goes for us. But no, the 18th down there. That's the last week. That bottom week is the last week before spring break. I have not decided yet because I haven't made the test yet. I am in the process of making the series test. Hope not. It's so far always 0. So far. So far we know nothing else other than centered at 0.
We got hit 25 after, right?
Yes. So far 0's all we've got. Yeah.
Can we just do this for test?
You know, I will tell you, there are people in Cal 2 who would argue this stuff you're doing right now is very difficult.
But this is to plug in.
I know, it's not too bad, right? Yeah, it's not too bad. No, I really think the way that we did this made it not too bad.
I like the introduction slash overview because it actually helps cement ideas.
Yeah, so you're not like, because imagine me just building it up from like, here's the formula, let's go, and you're like, oh, what am I doing? So you kind of have an idea.
What were you going to do without like, if they never go to summer conference?
I would have had to come up with something. I don't know.
You've done that. Let's formula. Let's go.
I don't know. I hadn't thought about it yet. But it was something I was nervous about teaching, and I'm not now. It was a good. He was good. Not at everything. Like,
How did you learn it? Did you just get thrown into it?
it was bad news. I didn't understand it until the second time I learned it.
So was it the hardest? Because I heard you say Cal 2 is the hardest.
It was the hardest topic in Cal 2 for me. Until I was a senior.
But ink is a lot more complicated, right?
A little.
She said it doesn't go up any higher, it goes down. Like it goes Cal 1, Cal 2, and then Cal 3, and everything else.
Yeah. It's branches. 3 dimensions.
Cal 4, whatever other math.
Really?
He didn't miss like any points in Cal 2.
That is a rarity.
He's happy.
I wonder if it's a professor.
He actually said it was. He said he didn't like it. He liked this Cal 2.
That must be it. The curriculum in Cal 3 is, if you understood Cal 2, you just throw a Z on the end and do it. Maybe their Cal 2 isn't as hard as other Cal 2s, and maybe.
I don't know. I thought he said it was hard, but he never had any problems with it.
Professor can make a big difference, you know, I mean.
He said this one didn't really teach, so just kind of like ramble a little bit.
That could be it. Okay, I'm just writing, but are we doing okay?
Yes. Just a while ago.
Good. What was above the 4? 2?
2 and then 1.
Hey, any questions about the 5th degree Taylor polynomial that models e to the 2x?
You just use that equation.
Okay, so let's look at the equation. What is the equation for e to the x from your calculus helper? Okay, so we would go all the way to the 5th, right? What would you plug in for x if you wanted e to the 2x? 2x. So where this x is, there would be a 2x. This would be 2x parentheses squared, right? And what is 2x squared? 4x squared. What is 2x cubed? 8x cubed. What is 2x to the 4th? And 2x to the 5th. So you could do that either way. Make sure the parentheses are there. But otherwise it will work out either way. Here are some common Mclaren series or Taylor polynomials centered at 0. They're common enough that you are expected to memorize them on the AP exam. That will be a good portion of your next mastery exam. You do not have to write this down if you don't want to, because it's on your, right?
Yeah, e to x goes minus.
Wait a minute.
I've been doing
I don't know. Which, no, it's the,
It says calculus on the very, very top.
not the little one though, is it? It's the one with multiple pages.
Oh yeah, it's the multiple.
That. So they should all be on there. I think they're all on there. However, what if you get to one and you do not know the answer? Do the Taylor polynomial expansion. The only one that would be slightly challenging on is arctangent, because y'all probably aren't as familiar with the derivative arctangent, but you should be. It's 1 over 1 plus x squared, right? So is the derivative of our tangent. Yes. Oh, maybe. I don't know. It's in that one. Maybe. It is in that one, yeah. It's, I don't know.
Can you tell us all the reference sheets that we should?
Yeah. We will have a mastery test, Joseph, that is a test of all. So you'll have...
Mastery to no masteries.
Yes.
It is the Armageddon.
No, like a test. Like a rate, yeah. Yeah, except we're going to add one more onto it. Okay, so... write the first four non-zero terms and the general term for the Mclaren series cosine of 2x. I have two options, but this time I'm going to go with the second option. The option of using the formula that I will someday have memorized and putting in the 2x. However, could you do it without that? You would just find the first four derivatives. Well, actually, we'll have to do more than that, probably. It does say the first four non-zero terms. On cosine, aren't you going to get several zero terms? Every other one is going to be a zero. Because the derivative of cosine, well, cosine of 0 is 1, but sine of 0 is 0. So every other term is going to fall off. Which is why the common Mclaren series, if you look at the cosine one, it doesn't have any odd values in it. Now, Claire made an amazing observation the other day when she said, hey, sine's odd, it's all the odd ones, and cosine's even, and it's all the even ones. Could you use that in your memorization of sine and cosine? That cosine is 1 plus x squared over 2 or minus x squared over 2 factorial. Why does it switch positive to negative every time? Because the derivative of sine and cosine every other time is going to change signs, because the derivative of cosine is negative sine. So it makes perfect sense. So the first thing I'm going to do is write the expansion of just plain cosine of x, just for reference. Now, it looks at first glance, and to the untrained calculus eye, people feel like this is a completely different formula than all the others we just did. But is it? It's just all the sine values were 0, so they aren't written.
How come it's negative plus and plus?
Where?
It doesn't, like on cosine and sine. It doesn't have them switching
After, well, it would be a negative. That next one would be a negative. See how it gives that general term and it's -1 to the end? So every time you have an odd exponent, it'd be negative, and every time you have an even exponent, it'd be positive. So cosine of 2x would be 1 minus 4x squared over 2 factorial. Do we agree? Plus 8x cubed over, nope, I'm lying, 16x to the 4th. Over 4 factorial. Minus 2 to the 6th power, is that 64? Yeah. 64x to the 6th over 6 factorial. 1, 2, 3, 4. I've got 4 non-zero terms. Done. Is this faster than finding 6 derivatives of cosine? Yes. Would it be wrong if you found 6 derivatives of cosine? No. Just take you longer.
But it would be wrong if you didn't have the zeros, right?
Well, you would, when you did the derivative of cosine, you would get sine of 0, which is 0. And so you would get your term to be 0. Does that make sense? So yours might look like 1 plus 0 minus, which would be okay. Okay. So centered at 0 means the polynomial fits really well around 0, right? Well, is there a chance we would rather have a better fit at a different x value? So, how to do that? This is the formula for the general Taylor series centered at x equals a instead of at x equals 0. Notice now all the derivatives are at the value a, not at 0. And then instead of just an x to a power, you have what? X minus a. That is the difference.
So kind of how we're plugging into 2x.
Very similar. Very similar. You are shifting. What would doing x minus a to something do to it? Shift it to the right a units. So we are now looking at the polynomial shifted over to the x value of a. I'm going to go ahead and pass out this worksheet. Do as much of it as you can before Monday. We will probably grade it on Tuesday, but we'll get more work. So, remember Mclaren, when it says Mclaren, what does that mean? Centered at 0. So if it says Mclaren, that means centered at 0. Nicholas, we grab one and pass. It's not.
Happy problem.
So if it says Taylor, the expected, now if it doesn't say centered anywhere, it probably means centered at 0, but just know Mclaren automatically means centered at 0. They're just called Taylor polynomials centered at. And Mclaren is a special case of Taylor polynomials centered at 0. So these, how do we feel about Taylor polynomials and either way where they're centered? Feel okay? Now, the common series that we're going to memorize, those are all centered at 0. So, centered somewhere else will be slightly different, but we can just do the formula. The ones that we're memorizing are Mclaren, or Taylor polynomials centered at 0. Imagine your life pre-calculator era, right? First of all, and then think about having to find the natural logs too. Yes, that's one of the things. Now, also consider derivatives and antiderivatives of things you don't know the derivatives and antiderivatives of.
Like that famous differentiation.
Right, there are a lot of things that we can't quite do all the way, but we can get an estimate. And so these allow us to approximate things that we struggle with generally. And what we'll learn in a couple days is we can get it within an error that you know.
And then we can try to.
Well, so say you are doing a project in engineering and you're accurate to 3 decimal points.
We don't care what
You can make this accurate to 3 decimal points.
you don't care what
Right.